Okay, we're going to spend a few days talking about stereoisomerism. This is a fairly complex topic in my way of thinking, and the IB has kind of stepped it up a little bit in the last set of curriculum documents and that kind of thing. So I've reproduced them here in your notes on page 313, and they give a lot of the little details about what it is that they want you to know, but it's all going to sound a little bit complicated if you just read it from there. So we're just going to go through, I'm just going to divide this up into a bunch of small sections. First section that we're going to talk about are conformational isomers. And this talks about the spatial relationship between the hydrogens attached to a carbon. And so what I've got here is I've made a little model for you to take a look at. I know it's kind of taking up most of the screen. But if we look at this model of just ethane, I've got this in a specific set of rotations where if we look end on, if you can sort of see that, all the hydrogens are more or less lined up. Okay, and if we look at that in the notes, that is given by what's called the eclipsed conformation. Okay. So the ethane could take on that eclipsed conformation where all the hydrogens are more or less lined up. Okay, I draw your attention a little bit here to this last one. This is called a Newman projection. Okay, and if you look at a Newman projection, you're looking at the two carbon atoms, of which you're interested in the groups that are coming off of that. You're looking at those lined up so you can see the two carbons. And so if I look at my model here, I can see, and if I just, you can sort of see that the two things are, the hydrogens are just slightly, in terms of the directions of that, just a little bit, well, they're generally lined up, but in a Newman projection to show that both of them are there, you just twist it a little bit. So that's the eclipse, just like an eclipse with the sun getting in front of the, or sorry, not the sun getting in front of the moon, getting in front of the sun, or that kind of thing, or the earth getting in the ways and that kind of stuff. Okay, so that's the eclipse. The other thing that you could get is the, whoops, went a little too far there, is you could get the staggered conformation, and you can see that this is quite a bit different. If I look at this from the end, okay, so we get, and I'm sorry, there's a little bit of focusing problems there, but if we look at the staggered position, we can see that that's almost opposite to the eclipsed. And there you go, you can see it in the Newman projection, that if you sort of imagine these hydrogens in your mind from the model. The question that you have to ask yourself is, which is more stable? And I'd let you think about that for a few minutes, like which is going to be more stable. And if we think about it, flipping the page, the conformation where the hydrogens, like we have to remember that there are electrons here. They're not just wooden pegs and that kind of thing. There are electrons there. So they're going to try and get as far away from each other as possible to get into a low energy conformation. And so you would see that the staggered is actually more stable than the eclipse version. Okay, so I would fill in your notes appropriately and have an idea of why that is. It does say the conference of ethane most stable would be obviously the staggered. At any one time, 99% of ethanes are in the more stable or staggered conformation. But it's not like you can have a container of just one over the other, because these things, you have to remember that these bonds are constantly changing, and the atoms are constantly spinning and rotating and doing all kinds of interesting things. We've talked again about conformers of cyclopropane and cyclobutane before. We mentioned that there was a problem here with cyclopropane because you're expecting to have a bond angle, or carbon expects to have, with four things attached, to have a bond angle of 109.5. However, in cyclopropane, we have a bond angle of 60, and in cyclobutane, we have a bond angle of 90. So there is some strain going on there, and unfortunately I don't have my any models here either, but I think at this time what you should try to do is make some molecular models of these things, and check this out for yourself. But if you flip over the page, you're going to see some diagrams where we see that in cyclopropane, the hydrogens are all necessarily sort of lining up in the same plane. And so that's going to create both an angular strain, and there'll be some torsional strain. It's going to want to twist. It's going to want to try and get to that conformation where the hydrogens can get farther away from each other. And so that's why the molecule is so unstable. And similarly with cyclobutane, if we look at this thing, and when you make one as a model, you will see that it's probably better to have 3 carbons in one plane and then have a 4th one slightly staggered out of that, and that will help take care of some of the torsional strain that's going on. That's all I wanted to say about that topic. Like I said, you should make those 2 models, or if you want, even make an ethane molecule and move it around. But there's some homework later on that you should do as well. Okay, that's all for now.